In our last class, we discussed about homomorphism and isomorphisms. So in this class also, we will talk more about the same thing, but with few very interesting problems or very interesting examples that will be very much useful for many competitive exams. Okay. So if you look at, so as you understand that we have suppose G1 and G2 are two groups, and suppose F is a homomorphism from G1 to G2, then few terms we have already explained, that is if F is homomorphism, and plus if it is injective, then we call it monomorphism. Monomorphism. Then if F is homomorphism plus surjective, we call it epimorphism. And if F is homomorphism plus bijective, we call it isomorphism. So that we all know. Okay. We also have seen that if F is a homomorphism, then kernel of F is a subgroup of G1, image of F is a subgroup of G2. Also, we have seen that kernel of F is a normal subgroup of G1, normal subgroup of G1. Okay, so this is my kernel of F. We have also seen that if kernel of F equal to E, then F is, what do you say? F is
Injective.
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 That means monomorphic.
Injective.
Very good. And the converse is also true. If F is a monomorphism, then kernel of F must also be, so this is G1, E of G1. Okay. Now, just have a look at simple result. Like suppose I have a mapping say from G1 to G2, and F is an onto mapping. So F is an epimorphism. Okay. Now consider a subgroup, say K. Let K be a subgroup of G2. Then F inverse K. So how do you define F inverse K? So F inverse K means something here. So all such elements G belongs to G1 such that F of G belongs to K. That means image of all those elements which goes into K. Okay, so this is my F inverse K. So I claim, or ask a question, F inverse K is a subgroup of G1. True or false? What do you think? There is no doubt that F inverse K is a subset of G1. I am asking you whether F inverse G is a subgroup of G1 or not. What do you think? True or false? Any guess? Wild guess? So how many of you think that it's true? Okay, let us try. Let us try direct proof. Yeah, anybody wants to say something? Okay. Let us try to see. Okay, first let me check whether F inverse K is empty or not. Claim F inverse K is non-empty. How do you prove that F inverse K is non-empty?
The identity always goes to identity,
Very
and
good.
K is subgroup of G2. Then
Yes. So
in F
if
inverse K,
you,
identity exists.
very good. So if you take the identity element of G1, so this is my G1, and if you make a F on it, so we know that homomorphisms send the identity element to identity element, then that will be E of G2. And K is a subgroup of G2. Note that K is a subgroup of G2. That means E G2 must be within K. So that belongs to K. Now you can understand that f of G belongs to K. So f of G belongs to K. So this is playing the role for G. That implies E of G1 belongs to F inverse of K. That implies F inverse K is non-empty. So this part is very formal. I mean, you need to always, whenever you want to have some group structure or ring structure or whatever may be, the first step is that the set must be a non-empty set. So this step says that this is a non-empty subset of G1. So first part is done. Next, what we need to show, that we need to take two elements from here. So let say AB belongs to F inverse K. That implies FA, FB belongs to K. What you need to prove? To prove A, B inverse belongs to K. So to show that to show that A, B inverse belongs to K, what do you need to show? You just need to show F of A, B inverse. Sorry, what do you need to show? To show not K. Okay, so I'll just again repeating. So take two elements from here, AB two elements from here, then that implies FA and FB belongs to K. What you need to show? To show A, B inverse belongs to F inverse K. If you are able to prove this, then that will help you to show that F inverse K is a subgroup of G1. Okay. So to show that this belongs to F inverse K, that means you need to show, that is to show F of A, B inverse belongs to K. So that's from definition of F inverse K. Now, what is this value? F of A, B inverse equal to F of A, F of B inverse, and we have already seen few properties of uh, things like FA into FB whole inverse. And you know that this is FA belongs to K, FB belongs to K, and this is a subgroup of G2. So FA into FB whole inverse must also belongs to K, as K is a subgroup of G2. Okay. So we are done. That implies A, B inverse belongs to F inverse K. So what it says? It says that F inverse K is a subgroup of G1. So what was our assumption, or what was our assertion? We made it. So this is true. Okay. So note that here important part is that what we assume here, that F is an epimorphism. Now the question is, did I use this fact epimorphism? Did I use this fact F is an epimorphism? Or F inverse K is always a subgroup of G1? Did I use this fact? Anybody? Okay, let's check again. So we have, so that's my question, whether we have used the fact that F is an epimorphism. If that is not required, then you can say that it is always a subgroup of G1. Okay. If it is required somewhere, then you have to impose this. So that's my homework. You need to check it, whether I have used somewhere the fact that F is an epimorphism or not. Okay. If it is not required, then if F is a homomorphism, then that will be sufficient. Then if K is a subgroup of G2, then F inverse K will always be a subgroup of G1. If this is an epimorphism, this property is not required, then only homomorphism will be sufficient.
Sir, if it is not epimorphism, then G2 may not be a group.
G2 is always a group. G2, I have given that. G1 and G2 are two groups. I have already given that G1 and G2 are two groups.
Okay.
Okay. So you need to check it. Okay. Now let us come to another question. So what we have seen that we have, so G1 and G2, say G1 and G2, and say this is an epimorphism. Okay. So this is a subgroup, say K is a subgroup of this. So this is, say, my, say, kernel of F, and say by some means this is my F inverse of K. So from the image, it seems that kernel of F is a subset of F inverse K. Now I claim that the same thing. My claim is kernel of F is a subset of F inverse K. See, I started with any subgroup of G1, right? And F is my homomorphism, which I assume that epimorphism. Now, my question is whether again this epimorphism will be required or not. That is up to you. That you need to check whether you can replace it by just by F a homomorphism, then also still the same problem or same property will be satisfied or not. But for the time being, I assume that F is an epimorphism. Okay. Now I am claiming that kernel of F is a subset of F inverse K. Okay. Can anybody be able to prove that? Okay. Let's start with this. Let X belongs to kernel of F. What does it mean? That implies F of X equal to E G of 2, and that belongs to K, because K is a subgroup of this. That implies X belongs to F inverse K. Then what it implies? That implies kernel of F is a subset of F inverse K. Now you see that this crazy things happens. You started with any subgroup of G2, and then you suddenly find that whatever be the kernel F, that will always be a subset of this F inverse K. Okay. So these two results will be helpful when we will talk about correspondence theorem, but I will teach you this correspondence theorem maybe at the end of the class. But before that, I am going to teach you, or I am going to give a lecture on the most important result on isomorphism, is known as first isomorphism theorem. So is this result clear? So what I give you the homework is whether this epimorphism is required or not. Can you replace the same result just by saying that F is a homomorphism? Then also will the same result hold? That's my question that you need to check. Okay. So now what I'm going to tell you is the most important result of isomorphism. Okay. This is known as first isomorphism theorem. So you can understand that since this is first, then there must be second, third, fourth, fifth, sixth, and seventh, etc. Yes, there are mostly 3 isomorphism theorems, of which I am going to give you the statement as well as the proof of the first isomorphism theorem. and you are requested to read the second and the third isomorphism theorem. Okay. Okay, let us have a look at what is the statement. Okay, let G1 and G2 be two groups, and F from G1 to G2 be an epimorphism. Then G1 quotient kernel of F is isomorphic to G2. Note that kernel of F is a normal subgroup of G1. As a result, you can have this quotient structure. So, G1 quotient kernel of F itself a group, and this result says that it must be isomorphic to G2. So, here what I have assumed that this is an epimorphism. Okay. I will ask you the understanding what will happen if this is not an epimorphism, that I will come to later on, but let us try to prove this. Is the statement clear to all of you? G1 and G2 be two groups such, and F from G1 to G2 be an epimorphism. Then G1 quotient kernel of F is isomorphic. So, this is isomorphic to G2. In some books you might have seen another equal. So, equal and then this sign, and sometimes it is only this. Both of them are equivalent. Okay. So, what I need to show that we need to give a mapping from here to there, and that mapping has to be a kind of homomorphism as well as bijective. So, let us try to define a mapping. And note that you have already given this mapping F. So, with this help of this mapping, I need to define a mapping from here to here. So, let us define a mapping phi from G1 quotient kernel of F to G2 by. So, can somebody tell me, say suppose G1 is a multiplicative group, can somebody tell me what the element of G1 quotient car F looks like? One element, some G car F. So, this, if this could be an additive group, then it could be plus. Since I am saying that it is a multiplicative group, so G into car F. And what it should be an element of G2, and you know that you have already given an element, a function which is a homomorphism from G1 to G2. Can anybody tell me how should I define this so that that should be an element of G2?
F of G.
Very good. F of G for all G car F belongs to G1 quotient car F. So, what we need to prove is that phi is well defined, phi is bijective, and phi is also a homomorphism. So, if we are able to prove all those things, then we are basically done. Then we are able to show that there exists a bijective correspondence between this and this, or you may say that there is an isomorphism from G1 quotient car F to G2. Okay. So, first let us try to see how this is happening. Okay, say two elements, say G car F equal to say G2 car F. If and only if when they are same, if and only if somebody, if and only if say G2 inverse G1 belongs to car F, if and only if F of G2 inverse G1 equal to E of G2. So, if and only if F of G2 whole inverse F of G1 equal to E G2. If and only if you can multiply both sides, that becomes F of G1 equal to F of G2. Okay. If and only if. So, what is F of G1? Again, you can go back to this. So, phi of G1 car F equal to phi of G2 car F. Note that what you have proved in one statement. So, this is everything is if and only if, right? So, this gives you the idea that phi is injective as well as phi is well defined. So, to show that this is injective, you need to start from here. This will suddenly imply this, that will give you the injectiveness, and for well definedness you should start from here and you must come to here. But since this is if and only if, so phi is well defined and injective. Okay. So, what you need to prove then, phi is surjective. So, let take some elements, say G2 belongs to G2. For this G2, you need to find some element of this set such that phi of that element should be equal to G2. Can anybody tell me what should be this value? Any idea, any guess? Note that you need to use the fact that f is given, and what is f? F is an epimorphism. Now, this is playing an important role. Now, tell me what should be that. So, you have taken some element from G2, then as f is an epimorphism, there exists some G1 belongs to capital G1 such that f of G1 equal to G2. What is then f of G1? By definition, f of G1 means this, that means phi of G1 car f equal to G2. So, for this G2, you have some element from G quotient car of f such that phi of G1 car f equal to G2. That implies what does it mean? That means phi is an epimorphism. So, we have already proved that phi is well defined, phi is injective as well as phi is so not epimorphism. So, phi is onto. Homomorphism not yet I have shown. So, that is phi is an onto mapping. Now, we need to prove that phi is a homomorphism, and that will in turn give you the idea that phi is well defined, phi is injective, phi is onto as well as homomorphism, and that will give you that phi is a isomorphism. Phi is an isomorphism. So, how to prove that? Phi is a phi is a homomorphism. So, for that you need to take two elements, let us say G1 car f, G2 car f belongs to G1 quotient car f. Then phi of G1 car f into G2 car f. By definition, we have already seen in case of quotient group, this is same as phi of G1 G2 car of f. And by definition of phi, this is same as f of G1 G2. Again, f is a homomorphism. So, f of G1 f of G2, and that will give you phi of G1 car f into phi of G2 car f. For all G1 car f, G2 car f belongs to G1 quotient car f. That implies phi is a homomorphism. As a result, phi is an isomorphism. Clear? Done? Is it okay? Any question? If you have, please let me know. Any question, anybody? Is it clear to all of you? Okay. So, if that is clear, let us now try to find some of the examples where we use this first isomorphism theorem. Okay. Okay. So, first one is, say, you all know that GL say 2R, you know this is a group. So, this is a multiplicative group, all 2 by 2 matrices, real matrices whose determinant value is non-zero. And we all know that R star, non-zero real number with respect to dot. Okay. Now, what I say, if you have SL2R, then that must be isomorphic. That means GL2R quotient SL2R is isomorphic to R star dot. So, wherever you will find this quotient structure, always try to use first isomorphism theorem. That will give you lot of extra help if you apply first isomorphism theorem when you are having this quotient structure isomorphic to something. So, to apply this, what we need to define? Can anybody tell me? To use first isomorphism theorem, how should I define from here to there? So, we need to define a mapping phi from GL to R to R star. And how it should be defined? Defined by phi of,
Determine.
yes, phi of A. So, A is a 2 cross 2 non-singular matrix that should be equal to date of A, right? Then you can check that this is a homomorphism, this is an onto mapping as well. Okay. So, this will be an onto mapping. How will you prove that this is an onto mapping? How will you prove that this is an onto mapping? Anybody be able to tell me? So, how to prove this is onto? To prove that this is onto, you need to take some element. Let say A belongs to R star. Can you find some element from this whose determinant value is A? Can you find?
Yes, A into identity.
Okay, that means if you have A into identity element, what is this determinant? A into identity element means what? Can anybody tell me what is this? A into identity element, you said like this, right? So, what is this value? Phi of A0 0A. And what is this determinant? Date of A0 0A. That should be how much?
Yes.
A square. So, this is not done, right? So, this is not will be a solution. Now, tell me what should be the solution then?
1 0 0 0
1 0
0 and 0.
1 0 0 0. Then will that be
No sir, no sir, no.
Okay, very easy. You can very easily, if you consider say A0 0 1, what is this determinant? Then determinant value
A.
A. So, for this A, you can find this matrix. Of course, this matrix. So, since A belongs to R star, so A cannot be equal to 0. So, for this matrix, this is an element of GL2R, and for this matrix, this is a phi of this matrix must be equal to A. So, this is an onto, and you can prove very easily that this is also a homomorphism. So, phi is also a homomorphism. Then by first isomorphism theorem, what you can say? GL2R quotient kernel of F must be isomorphic to R star. Now the question is, what is kernel of F? Okay. So, what is kernel of F?
So SL2.
Very good. So, all such A belongs to GL2R such that phi of A, that is equal to date of A, should be the identity element of R star. And what is the identity element of R star? that is nothing but 1. So all such matrix 2 by 2 real matrices whose determinant value is 1. And what is that? That is nothing but SL2R. Okay. So one way to prove that SL2, so this is very important from very competitive exams. So that means, so CARF is this. So from here, what will, so we have GL2R quotient SL2R is isomorphic to R star. Now this question may be asked in a different way, like prove that this is sometimes asked that SL2R is a normal subgroup of GL2R. So you do not need to make like H inverse belongs to something
Sir,
H.
kernel of a homomorphism is a normal subgroup, so
Very
we can
good.
say that.
You can directly say from here that this, if you have this homomorphism, then kernel, if you have this homomorphism, then kernel will be certainly your SL2R. As a result, you do not need to show like this, and that will certainly reduce lots of your time in competitive exam. So from here you can understand that SL2R is a subgroup of this. Clear? Is it clear to all of you? Good. So that's very interesting and quite important question. Okay. And in many competitive exams, you will find this question. Okay. So another important, let us try to have a look at this. Say, you all know, remember, I think Dn, right? You remember Dn? So this is basically, now you know the generated symbol. So it is generated through rotation and flip, such that we have this r to the power n equal to f square equal to how much?
Identity.
Identity, and there must be a relation between this. So Rf should be equal to f r to the power n minus 1. So this is known as dihedral group. For example, if I consider n to be, say, n to be 4, then we are actually trying to find all possible symmetries of the regular polygon with four vertices. That means a square. So this is a regular polygon with 4 vertices, that means square. If n equal to 5, then we are actually trying to find regular polygon with 5 vertices. Okay. So though it's not a regular, but assume that for abstract algebraist, it's very much regular, so you can assume anything. Similarly, for n equal to 6, it would be a hexagon, all possible symmetries on hexagons. Okay. So that will be given by this Dn. So if you remember, so can you tell me for D4, what could be all possible symmetries? Like we started with E, then R, then R square, R cube. You remember what is R? R is nothing but a rotation about the origin, about the center. So if this is the center, it's a rotation by how much angle?
90.
90 degree. Okay. And then r to the power 4 is E, because if you have R square means 180 degree, R cube means 270 degree, r to the power 4 means again you will come back to 360 degree, that means again you come back to the original position. That's why r to the power 4 equal to E. Now again it's flip. Flip could be anything, like symmetry is about this. So this will come here, this will come here, or symmetries about this will go here, this will go here, or even symmetries about diagonals. So they are the all possible symmetries. So if you consider any one of them as f, suppose this is your f, then you can understand that all the remaining flips can be generated like this: Rf, R square f, R cube f. Okay. And if you have flip like this, and if you make double flip, then it will again come back to the original position. That's why f square equal to E. Okay. And the relation is Rf equal to f r to the power n minus 1, that means R cube. and that is why this is not a commutative group. So we have already seen that order of D4 is 2 into 4, that is 8. D4 is a non-commutative group, non-commutative group. So there is no point of this to be a cyclic group. So you can understand very well that this is not generated by a single element, but there should be at least 2 elements to generate this group. So basically they are the generators. Okay. So order of Dn is how much? Order of Dn is how
2n.
much? 2n.
2n.
And if I tell you Dn is a non-commutative group, true or false? True or false? Anybody? Dn is a non-commutative group. If I ask you, if any question, if you get this, then what would be your answer? True or false? Yeah, it's very easy.
Sir, true.
For n more than 2, it is true.
Yes, if this is the statement, then it's false. Why this is false? Because for n equal to 2, you see that Dn is on how many elements? All possible symmetries with. So Dn, that means Dn equal to 2, this is isomorphic to, do you able to say that how many elements are there in Dn?
4.
What are they? In D2, how many elements are there? So all symmetries with this. How many? All symmetries? There are only 2 symmetries. So this is isomorphic to Z2. So only this will come here and this will come here, or it will be as it is. That means that is the E, or it will come here, this will come here. Okay. So basically this is n greater than equal to 3. So for the sake of completeness, I must mention n should be greater than equal to 3. So for D2, the result is isomorphic to Z2 and it has only 2 elements. So it must be cyclic. So it is commutative. So in general, Dn, if no n is given, for n greater than equal to 3, if this is the statement, then this would be true. Otherwise, this would be, for general statement, it's false. And so that is why in many competitive exams, when you are within the exam hall, then you feel that you did well. But when you come out of the exam hall, you find that few of the questions you just missed because you forgot about few exceptional cases. So you have to be very, very careful while answering this kind of questions. Okay, they are easy. You all know the answers. But at the time of exam, sometimes it does not click. And that is the reason why for most of the cases, you are unable to perform what you are basically potentially in. Okay, so please take care about this kind of facts. So you have to read quite carefully. Okay, so let us try to define few of these mappings. Okay, let's say for Dn, I am assuming that n greater than equal to 3. Okay, so I am trying to define a mapping from Dn to say Z2 by, so this is generated by 2 elements, right? Dn, one is rotation, another one is flip. So I need to send somewhere. So let's first put all rotations to 0 and flip to 1. So 1, 0 mean class 0 and 1 mean class 1. Okay. So will this be a homomorphism? Question. Is phi defined like this? Is phi a group homomorphism? What do you think? True or false? If I define like this, what would be your answer? True or false? It's not very difficult. Okay, so how to check whether this is a homomorphism or not? That must satisfy the properties. What are the properties? It says that r to the power n equal to e equal to f square, and rf should be equal to f r to the power n minus 1. So if on phi of this that will be satisfied, then we are happy. Okay. So let's first have a check of what is r to the power n. Can anybody tell me what is r to the power n? So if this is a homomorphism, then it should be n of phi of r, because that right side is an additive group, and if phi is an homomorphism, then it must satisfy this property phi. So this is r into r into r n times, and that will be phi r plus phi r plus phi r n times. So this will be how much? Phi of r is 0. So n into class 0, that means class 0. And we have already seen that phi of r to the power n, that means e. So this is phi of e is 0. That is good. So it's satisfying the property of homomorphism. It's sending the identity element to the identity element. So it passed for this. Okay, let's try with phi of e equal to phi of e square, sorry, f square. And what is phi of f square? 2 of phi of f. Let's see, what is 2 of phi of f? Phi of f is 1, so 2 of phi of f, that is also 0. Okay, so it sending e to e through f. So this is also satisfied. Now the crucial one, what is this? So phi of rf, and if this is an homomorphism, then it must be phi of r, sorry, it must be phi of r plus phi of f. So what is phi of r? Phi of r is 0, class 0, plus class 1, and that is class of 1. Okay, let's see what is phi of f r to the power n minus 1. If this is an homomorphism, then it must be phi of f, it must be phi of f plus n minus 1 phi of r. Okay, so what is phi of f? This is 1 plus n minus 1 into class 0, and that is also class 1. Okay, so that is also satisfied. So we can say that if that could be a homomorphism, then it satisfies all the properties. Now, can anybody tell me what would be the kernel of f? Kernel of f, kernel of phi, sorry, kernel of phi, kernel of phi. What is kernel of phi? Quickly.
They're all rotations.
Yes, so the subgroup generated by the rotations, yes, all rotations. So kernel of phi is nothing but all of them. So r, so start with e, r, r square, r cube, up to r to the power n minus 1. So all rotations. You can understand what is why phi of, what is phi of r square? This is 2 of phi of r, and phi of r is already 0. 2 of, so it's already 0, plus 0. So r square is also within the kernel of f. Similarly, r to the power n minus 1 is also there. Will be any of them, will any of the flips be equal to 0? Phi of any of the flips, that means r to the power, say, I into f, will that be an element of this 0? What does it mean then? I into phi r plus phi of f. Now this value is already 0, so class 0 plus phi of r, this is class 1, so that will be always 1. As a result, no flip like f, rf, r square f, up to r to the power n minus 1 f, none of them will be, phi of none of them will become, phi of none of them become class 0. Okay, so This is the only thing. So you can understand that this is nothing but the subgroup generated by R. Okay. So finally, what you can write like this, your Dn quotient, this R is isomorphic to Z2. In other words, you can say that, so this is your Dn, this is your Dn. Within this Dn, you have a copy of, so this is isomorphic to what? This is isomorphic to what? So this is a cyclic group, right? This is a cyclic group of order, how much? Order n. So that must be isomorphic to, we know that any cyclic group of order n is isomorphic to Zn. So what you can think that within Dn, a copy of Zn is there. So this is nothing but same as the cyclic group generated by the rotations, and that is isomorphic to the cyclic group Zn, and that's very interesting. That's why you can understand that within Dn you have already a kind of cyclic group inside as a copy of Zn, which is inside Dn. Clear? Is it clear to all of you? Very good. Okay. Okay. So now let us try to extend the same example, but with a little different way. Okay. How? Okay. Let us try to define a mapping Dn2. Instead of Z2, let's go to Zn. Okay. Defined by, so as usual, this is generated by rotation and flip, and phi of r, suppose I am giving it to 1, and phi of f I am giving it to 0. So in my previous example, it was phi of r was 0. If you go back to the last example, then it was phi of r was 0. So here the phi of r was 0 and phi of f was 1, but now I am just changing the other way around to phi of r is my now 1 and phi of f is 0. So the question is whether with this, with respect to this phi, whether that forms a group homomorphism or not. So as usual, we know that r to the power n equal to f square equal to e, and rf equal to f r to the power n minus 1. And let's see all these properties are satisfied with this phi or not. Okay, first let phi of r to the power n. What is this value? This value is n of phi of n, and just now we have seen that n into phi of r, and just now we have seen that what is phi of r is class 1. So this is class of n, and class of n in Zn must be class of 0. Okay, so this is my phi of e that goes to 0. So this property is satisfied. Now let's see what's happened with phi of e equal to phi of f square. This is 2 of phi of f, and phi of f is already 0, so that becomes 0. So this property is also satisfied. And now let's check what is nice property here. So phi of rf, if it would be an homomorphism, then phi of r into phi of f, and since this is 0, so ultimately this is 0, interestingly. On the other hand, what happens with phi of f r to the power n minus 1, and that becomes phi of f into n minus 1 into phi of r. So phi of f is 0. Okay, phi of f, so this is plus, sorry, this will be plus. Yeah, so 0 plus, sorry, this is, oh, I done a little mistake here. So phi of r into f should be phi of r into phi of f, That means phi of r is 1 plus phi of f is 0, and that becomes class of 1. Okay, and here it will be phi of f is 0 plus n minus 1 into phi of r, that is class of 1. That means class of n minus 1. Now you see that when class 1 equal to, if this is the case, then phi of fr, since they are same, look at this, if they are the, if this, since they are the same, to have this property, phi of this must be equal to phi of this. That means class 1 should be class n minus 1. What do you think? Do you think that this kind of, this is a homomorphism? So the question is phi a group homomorphism? True or false? What do you think? Any idea, any guess? Any guess? Can you think of any value of n for which class 1 and class n minus 1 are the same? If that is the case,
Two.
then only this will happen. Any guess?
The 2.
Two.
Exactly.
2.
So you can understand that this phi will be a homomorphism if and only if n equal to 2. If n equal to 2, then this value will also be 1. So unless, so this phi will be only a homomorphism if this is from this to this. If n is not equal to 2, then phi can never be a group homomorphism. That means if in other way, if n is greater than equal to 3, phi is not a group homomorphism. Clear? Everybody understood? Very good. Again, if we go little beyond, again very interesting property. If we consider, let us try to have a look at what happens phi from D2n to say Z2. What happens when phi is from D2n to Z2, say defined by, so as usual, phi of r goes to class 1, phi of f goes to class 0. See, same as before, but here in this case it was both of them were n. Now I am modifying it a bit. I am putting it here D2n. So this is my D2n, and here this is my D2, sorry, Z2, and I am defining like this. Okay, let's try to have a look what will happen here. So again, we'll have what we'll have? We'll have phi, so r to the power n equal to f square equal to e, rf equal to f r to the power n minus 1. So let's see if these properties are satisfied or not. Okay. Can you tell me whether this is satisfying or not? So phi of r to the power n equal to n phi of r, and that is same as n okay, n phi of r. What is phi of r? This is 1. Okay, and yeah, so this is class n. Okay, so this is 2n. Okay, so I did a little mistake here. So what we need to do, it's not n, but I need to check with 2n. So now my group is D2n to Z2. So we need to check this properties. Okay. So how to check this properties? Then, so this is not R. So this should be 2R. Okay. So I'll just make it again.
Excuse me, sir.
Yes.
So can I please ask you a question about the
Yes.
last thing?
Yeah, please.
Sir, can I just move the screen a bit upward? Yeah. So in the right hand side you wrote now, so equals to n equals to 0. Why did you write n equals to 0? Like in
Sorry.
the right hand topmost side.
Yeah.
This one, yes.
Yeah. So because yeah, so this is 0 because this class n where in Zn, not in Z2. So class n in Zn means what? It should be class 0. Clear now? For
Yes,
example,
sir.
in Z5, what is the value of class 5? This is same as class 0. Clear?
Okay, sir. Okay, sir. Yes,
It
sir.
was
Thank you, sir.
not 2, it was Zn. Okay. Okay. So let us again have a look at this same problem or same properties are satisfied or not. What are the properties? Properties are r to the power. So instead here it's r to the power not n but r to the power 2n, right? It should be r to the power 2n equal to f square should be equal to e, and rf should be equal to f r to the power. What should I write here? R to the power
2n minus 1.
2n minus 1. Very good. So let's check. So phi of r to the power 2n, that should be equal to 2n of phi of r. And what is this value? 2n of class 1. So this is even number, so it has to be 0. So this property is satisfied. So phi of e equal to this, and this is class 0. So again phi of e equal to phi of f square equal to 2 of phi of f, and that is already 0. So this is 0. So these two properties are satisfied. Now let's check with this. So phi of fr equal to phi of f plus phi of r, and what is this value? Phi of f is 0 plus 1, and that is equal to class of 1. Now let's check with f, sorry, it should be rf, not fr. It should be rf anyway. So it has to be like this, and okay, and this is f r to the power 2n minus 1. What is this value? It should be phi of f plus 2n minus 1 phi of r. So phi of f is 0, and this is 2n minus 1 into class 1. So this is an odd number anyway, right? So this is an odd number. That's why this value will be 1 in Z2, because in Z2 1 and minus 1 is same. So you can see that both of them, these values are 1. So this property is also satisfied. So this will be a homomorphism, no doubt about that. Now can anybody tell me what is kernel of phi? What is kernel of phi? Quickly. And that will lead you to an interesting idea. What is kernel of phi? Okay, let's see. One element I am giving you an hint. E is already there.
Sir,
So the
E and F.
E and F.
Yes, sir.
Okay. Anything else? Will R square be there? Will R square be there?
Yes, R squared.
So R square will also be there. R to the power 4 will be there. R
Yes,
to the
sir.
power 4. because all even powers will be there, because this even number will come in front in the additive form. So R, so this is 2n minus 2. So all even numbers will be there, and then this is odd number. But will f will be there? And then anything else? Will r square f be there? R square f will be there.
Yes, sir.
R to the power 4 will be there.
Yes, sir.
And then you can understand r to the power 2n minus 2 f will also be there. Now let us have a look at very interesting observation. Okay, so if I rewrite all of them, then how it should look like? It should be e r square r to the power 4 r to the power 2n minus 2, and then f r square f r to the power 4f and r to the power 2n minus 2f, right? Okay, now just assume that r square equal to say s. Okay, then I can write it e s square s cube s to the power n minus 1 f sf s square f s to the power n minus 1 f. Okay, and then let us try to find the relation. What is s to the power n? S to the power n is, what is this? R to the power 2n. What is R to the power 2n? At the initially we have written R to the power 2n was my e. So this is my e. F square is already there in my previous, so f square is equal to e. Now what is the value of Rf and the relation between, sorry, sf and f s to the power n minus 1. So what is sf? This is r square f, right? And what is this? F r to the power 2n minus 2. Now can somebody tell me what should be this value? Okay. Is it equal or not equal? Tell me. Is this equal or not equal? What is given? So in the given condition, it was Rf equal to this, right? So Rf, so my Rf, given that f r to the power 2n minus 1. Now multiply both sides from the left by r, then r square f equal to Rf into r to the power 2n minus 1. What is this Rf value? You can put the value of Rf here. So this is f r to the power 2n minus 1 into r to the power 2n minus 1. Now can anybody tell me what should be this value? F of r2n into r of 2n minus 2. I can write, I can just make r to the power minus 1 here, and just r to the power 2n into r to the power minus 1 into r to the power 2n minus 1, and then one step, I just make a step jump. What is this value? R to the power 2n is how much? Is e. This value is e. So f r to the power 2n minus 2. So f r to the power 2n minus 2. And what is this value? This value is r square f. So they are same. That means sf equal to f s to the power n minus 1. Now from here, can you tell me what is this Kf? So this was my Kf. I started with Kf from here, and ultimately I came to this set with this relation. Now Can you tell me what is this? What is this Karif?
DN.
Exactly. So this is nothing but Dn. Then what you get ultimately, you understand that d of 2n quotient d of n is isomorphic to Z2, because it has 2n, it has how many elements? 4n elements, and it has 2n elements. So as a result, it will be a group of order 2. That is not of good, I mean, that is not of very surprising result. But the interesting fact is that if n is greater than equal to 3, then within D2n, you will have a copy of Dn. That means D6 contains D3 as a subgroup. Not only a subgroup, as a normal subgroup. So D12 contains D6 as a normal subgroup. And that's quite interesting. So sometimes this question is being asked whether Dn is contained in D2n or not. And you can see that from here you can very easily explain how D2n contains Dn as a normal subgroup. Is it clear to all of you? Clear? Okay. Now let us have a very interesting geometrical concept or a geometrical image. Say I want to define a mapping, say from F homomorphism from, okay, let's all I denote it by phi. So let it phi from say from Z to C star. You know C star. So set of all complex numbers, non-zero complex numbers with respect to multiplication, and this is my Z plus defined by phi of n equal to say 2 to the power n into I to the power n. Okay, so this is my phi of n equal to 2 to the power n into I to the power n for all n belongs to Z. First tell me, question, is phi a group homomorphism? True or false? Quickly. Is phi a group homomorphism? Let's check. So phi of n1 plus n2 equal to 2 to the power. So this means 2i to the power n1 plus n2, and this has to be 2i to the power n1 into 2i to the power n2, and that should be equal to phi of n1 into phi of n2. That implies phi is a group homomorphism, right? Okay. So what is kernel of phi? So just write down go by the formula. So what is this? Kernel of phi means all such elements n belongs to Z such that phi of n should be, what is the identity element? 1. So all such element n belongs to Z. What is phi of n? 2 to the power I to the power n, that should be equal to 1. And then what should be the value of phi? For which values of this n? Suppose n is 2. Will it be 1 anytime? Because it will be ultimately 2 to the power n. Since 2 to the power n is there, and this I value will be either plus minus 1 or plus minus I, but the point will be here it is 2 to the power n. For n value 0, except for n value 0, nothing will make this 2 to the power n as 1 or minus 1 or I or minus I. So this should be equal to 0, nothing else. Okay. So that is not very important. So the point is, how will you draw this image? That is quite interesting. Okay, let's draw it. Okay, let's draw it here. So this is my x-axis, y-axis. So this is my, say, real and this is imaginary. So this is my I and this is, say, real. Now for n equal to 0, what is this value? N equal to 0, this value will be 1. So this is my 1. So my point is this. For n equal to 1, this value is 2i, right? So this is my I. So sorry, I put it 0 here. I just put it. So this is my 1. For I equal to, so n equal to 2, this value is, sorry, n equal to 1, this value is 2i. That means 1, 2. So this is my 2i, right? So this is my 2i, this is my 1. For n equal to 2, this value will be 4. I square means minus 1, minus 4. So 1, 2, 3, 1, 2, 3, and 4. So somewhere here. Now, for n equal to 3, this value will be 8 I cube. I cube means minus 1. That means minus 8i. So like this 1, 2, 3, 4, 5, 6, 7, 8, somewhere here. Now if n value is from z, right? So it could be minus 1 as well. So if it is minus 1, then it will be 1 by 2 to the power I. And what is this value? This is minus of, if I put it minus of half I, that means I by minus I by 2. That means something here. So now you can understand that the integers are being plotted, and this is like this, and you can go like this. So now you can understand that you are plotting basically these values of n. The integers are being plotted in a spiral way like this. You can understand that this could be huge, whereas if I make the values of n less than 0, then it will go near to the center in a spiral way. So that's a very interesting idea, to plot the integers on the complex plane. That's very interesting. Okay. So there are plenty of such examples where you can use this results, and there are plenty of others. So just I am giving you a kind of example or exercise. Maybe you can think of like say maybe from here, say from D6 to maybe S6. Okay, it can be done from Dn to Sn, doesn't matter. So D6 means you have a regular hexagon. Say this value is 1, 2, 3, 4, 5, 6, and say take any of the symmetry. Say I am taking this symmetry. That means here 1 goes to 4, 2 goes to 3, and 5 goes to 6, or 6 goes to 5. So this symmetry can be represented by this permutation. Okay. So what I'm going to do is that I'll just put this R. So my R, phi of R, it goes to a cycle 1, 2, 3, 4, 5, 6. So that's an element of this. And phi of flip, I'm doing this permutation 1, 4, 2, 3, and 5, 6. So it's my homework. Check whether phi gives you a group homomorphism, gives you a group homomorphism. Okay. If so, then what is car of phi and what will be image of phi? So both the things I need. In my next class, I will ask you. Okay. So it's you will see that that will certainly be a homomorphism, and then you need to check what would be the kernel. I guess the kernel will be the identity element only, and then you need to check what would be the image. So you can understand that the image will be kind of generated by these two. Okay, then you can try to find what could be the cycles. That would be little tedious job for you to do, but it is good to work with this kind of permutations and all. Okay, so I have already shown you many things. Now just I will modify a little bit about the first isomorphism theorem. Is just a kind of corollary. So what I had in first isomorphism theorem, you had two groups, say G1 and G2, and F was my homomorphism, F was my epimorphism, right? If F is not an epimorphism, then what will happen? Then it will be exactly the same way, but if F is only a homomorphism, then the statement will be G1 quotient kernel of F must be isomorphic to. Can anybody tell me what would be the statement?
Image
Image,
F.
Very
of
image of F. Okay. So you can understand that if this is epimorphism, then image of F must be equal to G2, and that was the statement of first isomorphism theorem. So if this is epimorphism, then image must be equal to G2, and that was the result. Okay, so it's just a simple remark, or you can think of not always that it will be a group homomorphism or epimorphism. Okay, now again I am going to deal with another very important result, that is known as correspondence theorem. Correspondence theorem. What it says? Okay. It says that, again the same format, let F from G1 to G2 be an epimorphism. Mind that this is epimorphism. Then F induces an one-to-one inclusion preserving. Inclusion, what do you mean? I will explain. Inclusion preserving mapping, the homomorphism mapping from the set of all subgroups of G1 containing car of F and set of all subgroups of G2. Okay. So what does it mean? It may little longer, but it's not very difficult to understand. Suppose you have a group homomorphism, epimorphism is there. F is an epimorphism from G1 to G2. So this is my car F. What it says, there will be, take any subgroup, say here, any subgroup, say H1 from G1, then suppose this H1 contains car F, then for this H1, there will be another subgroup, say H2 from G2. I mean, for this H1, there will be a unique subgroup H2 from G2. Okay, that is, it says. Then that homomorphism induces an one-to-one inclusion preserving mapping from the set of all subgroups of G1 containing car F. If you take any subgroup of G1 which contains car F, then for that subgroup there exists a unique subgroup H2 of G2. That means there is a one-to-one correspondence, and it says that it's an inclusion preserving. What does it mean? If say H and K are two subgroups of G1 such that H1 is a subset of, say H is a subset of K, then okay, G1 containing Karef. That means both H contains Karef, K contains Karef. Then F of H is also a subset of F of K. Okay, that is, it is the meaning. So you take any two subgroups from here, say H and K, both of them, they must contain Karef. Then if you apply F, so for this K, there must be here something, say for this K1, suppose I take this K1 and H1. For this K1, there must exist some unique subgroup K2 in G2. For this H1, there must exist some H2 in G2. Since H1 is a subgroup of K1, here also after putting F of H1, F of H1, that is also a subgroup of F of K1. Okay, so that is the inclusion preserving mapping. So the proof is not very difficult. I'm not going to give you the proof, so you can find it in any standard book. If you are unable to understand, please let me know in my next class, then I will try my best to make you understand. Okay, so again, I am just giving, once again, I'm trying to explain the same thing. The correspondence theorem says that suppose you have, say, a group epimorphism from here to there, say F is an epimorphism. So this is your card F. Take any subgroup from here, say H, say this is my G1, this is my G2. For any subgroup which contains card F, there exists a unique subgroup here, say K of G2. And other way around, take any subgroup K from here, there must exist a unique subgroup H which contains card F. Okay, so there are two sets, say H is my one set, say H is all subgroups of G1 containing card F, and this is my K, all subgroups of G2. Okay, it says that there must be an one-to-one correspondence. That means these two sets are bijective. For each element here, you will find a unique element here. On the other hand, if you take any element from here, you will find a unique element here. So only thing is that for H, the script H, all the subgroups must contain this kernel of F. Okay, so how to define then? So you need to define a phi, a mapping from H to K. How do you define? So phi of, so I need to show that this is a bijective mapping. So phi of one element is, say, H. So H is a mapping which contains card F. How do I define this? Anybody be able to say me? So F is given. How will you find? What should be phi of H? Anybody tell me what should be phi of H? Using F. F is already given to you. What should be phi of H using
F
F?
of H.
Very good. F of H. We have in our class on isomorphism, I think in my last class I have already defined that F of H is a subgroup of this, right? So exactly. So F of H for all H belongs to script H. Now you need to show that this phi is a bijective mapping, and there you need that this is an epimorphism. So take any element from here. So what you need to show, that this is injective. What you need to show? One, this is injective. Then you need to show surjective, and then you need to show inclusion preserving. Inclusion preserving means take any two subgroup like this. So from here, that means both kernel F is already contained there. It contains car F, this also contains car F. Okay, that should imply F of H1 is also not F, phi of H1 should be phi of H2. So what is phi of H1? Phi of H1, just now we have seen that is F of H1 is a subset of F of H2. Okay, these three things you need to prove. So when you need to prove, you need to, at the very beginning of my class, I have already given you a hints. So to show that this is surjective, what you need to take? You need to take some element from here. Say K is an element from here. So you need to find some element here of which if you apply phi, that should give you back this element K. Can anybody tell me what should be the, suppose K belongs to script K. What should be my this side element which contains car F? At the very beginning of my class, I have already given you the hints. Anything? What should be the element from here? By using F, you need to do that. Anything? From here, you
F
need to.
inverse K.
Very good. If you remember, F inverse K was a subgroup of G1 which contains car F. And that's why I just proved at the very beginning of my class that F inverse is a subgroup of G1 containing car F. Now you understand that why I have given epimorphism there. Whether for that proof epimorphism is required or not, that you need to find. Now it will be quite clear to you that in this statement epimorphism is given, and epimorphism may play an important role here, but my question was whether that also the same epimorphism, whether that could also be useful in proving that result, that F inverse is a subgroup or not. Okay. So by using this result, you can very easily prove that phi of this F inverse, phi of this F inverse K will be K. That you can prove. And if you will able to prove that, then that will be surjective. Injective part is also easy, and inclusion preserving is part is also easy. So this is known as correspondence theorem, and interestingly, this is not for any, I mean, this is also true for any normal subgroup. Instead of considering H to be any subgroup, if you consider H to be any normal subgroup containing car F, then for that subgroup, you will also have a unique subgroup in this side. Okay, and similarly, if you have any normal subgroup from this side, then there will be a unique normal subgroup from this side which contains car F, and so that is known as correspondence theorem. Okay, so any other questions? If you have, you can ask me. So there are plenty of nice examples that you can think of, like Q quotient Z is isomorphic to. Now you can think of what should be your things. There are many things by using first isomorphism theorem you can prove. Okay, so I'm leaving here. Any question? If you have, you are free to ask me.